Hi, this video is about Hess's law. We're going to use delta H's of reactions and we're going to add equations together and get a delta H for a new reaction. So, Hess's law states that if a reaction is carried out in a series of steps, the delta H, or the enthalpy for the overall reaction, will equal the sum of the enthalpy changes for each individual step. So what are we trying to do here? We're trying to get a set of chemical equations arranged in such a way so that when you add them all together, things will cancel out except for what you want in your overall final equation. So we need to learn how to add equations together, and it's very simple. So basically what we do is all the reactants. So here we have two separate reactions. So here's the combustion of methane reaction, and the second one is the condensation reaction for water. And so they're two separate reactions, and we can add together all of the reactants from the two reactions. So we have CH4 and 2O2 and two waters that are in the gas phase, and that's going to equal CO2, two waters that are in the gas phase, and two waters that are in the liquid phase. So if you see what I did here, I just put all the reactants together and all the products together. Now, if there's anything that appears on the reactant side and the product side, they can cancel each other out. And you have to be careful and look at the phase. So here we've got water that's a gas, and we actually have two, and there are two over here that is in the gas phase. So we can cross those out. But the liquid water would stay because there's not liquid water on the reactant side. So adding these two equations together, we would have CH4 plus 2O2 yielding CO2 plus two liquid waters. So again, this is just summarizing what we do when we add equations together. And the final equation is called the net equation. So the sum of the reactants of all the equations is placed on one side, the sum of the products is on the other side, and any quantity that appears on both sides of the arrow will cancel each other out. And you have to pay attention to the state and also to the quantity. So if you had 2 moles of water on one side and 1 mole of water on the other, you could cancel 1 mole from each side, but not, you would still have 1 mole of water left on the side where you had 2 moles. Okay, so this is quite powerful. Enthalpy is called a state function. That means that the delta H, it does not depend on the path between the initial and final states. You can calculate the delta H for anything as long as we can find a route for which the delta H is known for each step. So we've got a few rules that we have to play by, and these kind of go back to our last video. If you change the reaction around, and we can do that, we can flip and make the products the reactants and the reactants the products. What do you do with your delta H value? Well, you just change the sign. If you multiply a reaction by a number, and we can do that, you have to multiply the value of delta H by the same number. And again, pay attention to the states of the products and the reactants. Now, here's a problem. We want to calculate the enthalpy for this reaction. So this is our final reaction. What is delta H for this particular reaction? And here are the equations where delta H's are known. We know that nitrogen and oxygen goes to two nitrogen monoxides, and the delta H for that is a positive 180 kilojoules. It's an endothermic reaction, and it's classified as a synthesis reaction. Look at this reaction. It's a decomposition reaction, and it's falling apart to form 2NO and O2. It is also endothermic because of the positive value of its delta H. Now we know the delta H's of these reactions. We want to manipulate these equations so that when we add them together, we get this final equation. So I look here, nitrogen's a reactant, and I look down here for any place where there's N2, and it's in this first reaction. So I don't see it anywhere else There's one nitrogen. I'm going to not multiply this by anything, and I'm not going to flip it. I'm not going to do anything to this first reaction because I need that one nitrogen on the reactant side. All right, I need to have 2O2 on this side. I don't want to multiply this by 2 because I don't want 2 nitrogens yet. Let's see, our product is 2 NO2s. The only place I see NO2 is in reaction 2, and we have 2 of them. However, it is a reactant. So we need to flip this reaction around. So this reaction is going to become 2NO, which is a gas, plus O2, which is a gas, is going to yield 2 NO2s. And what do we do with the delta H when we flip an equation? Well, it had been endothermic, but now that we've reversed it, we change the sign of delta H, and it's now a negative 112 kilojoules, and our reaction this way, which is a synthesis reaction, is exothermic. Okay, let's see if that does it. So we have flipped this equation. I don't have a lot of room on this slide. Okay, so let's see. N2, great. NO, it's a reactant here, and we've got 2 of them, and it's a product here. So we can cross them out because they're on opposite sides of the arrow, okay, when we're adding these together. We have 1O2, 2 O2s on the reactant side. Because they're on the same side of the arrow, they're both reactants, we're going to add them together, 2 O2s. Yields, and then the only thing left on our product side is 2 NO2s. So when we add these 2 equations together, once we have flipped the second one, we get what we're looking for, this net equation here. All right, so what's the delta H for this equation? We added these equations together, so we're going to add their delta H's together. So it's 180 plus a negative 112. So I believe that is going to be 68 kilojoules. And so it's still positive. This is now the delta H for the reaction, and it's an endothermic reaction. All right, so what I would like you guys to do is to try this problem. It's actually kind of a fun problem. So you're trying to get the delta H for this equation here. So 2 borons that are solid plus 3 hydrogens that are gases yields B2H6 that is a gas. And notice we would classify this as a synthesis reaction. Here are our delta H's for, we've got one reaction here, another one here, another one here, and another one here. So go ahead and try this, and we're going to start class with this tomorrow. All right, have a good night.